This is Richard Walker from Elucidate. Welcome to this second video in machine learning. Here we're going to examine decision trees. These are perhaps one of the most simple, intuitive, yet most powerful techniques in machine learning. They're most often used as classifiers to identify which group or class some input data should belong to. We're going to use them to identify which loan applicants are most likely to default. But they can also be used for regression tasks, where we want to predict an output number from an array of input parameters. Decision trees are an example of a supervised learning algorithm. We train them with some data that includes a target variable, whether a borrower defaulted or not. The decision tree learns to ask a series of binary yes-no questions on the rest of the training data that allow it to arrive at the correct classification. While some AI techniques deliver impressive results, the way they achieve their performance is often unclear. People are naturally suspicious of black box AI. Neural networks are a great example here. In contrast, decision trees are white box solutions. You can see each rule in plain English. Everyone can understand how the tree is classifying the data. To illustrate this, let's pull up our loan default dataset and apply a decision tree to it. We'll get rid of the account ID and the sparsely populated 90 days bad rating flag. We can drag in a decision tree and then a tree viewer. Here we see the decision tree as a series of binary yes, no, true, false, greater than, less than questions. We'll spend most of this video talking about how the tree forms an optimum set of questions and in what order. But before we do that, let's familiarize ourselves with the structure of the tree and some of the information in the tree viewer. This view shows a tree depth of 6. There's a depth control on the left, which we will look at shortly to increase or decrease the number of questions posed by the tree. The top node is called the root node. This contains all of the data in our loan default dataset. It only has data flowing out. Further down, you can see leaf nodes. These only have information flowing in. A leaf node will form when specific criteria are met. This might be because the maximum depth of the tree has been met, or it might be because it's a pure node, only containing data in a single class that can't be divided further. In this case, that would be a node that contains only defaulters. Here's an example. Or only repayers. An example is highlighted here. The tree viewer has several ways to show the purity of each node. Firstly, it uses color. Deep red shows a pure node containing only defaulters. Deep blue shows a node containing only repayers. Nodes that contain a mix of defaulters and payers are colored on a blue-red spectrum based on the mix of payers and defaulters in that node. Secondly, a small pie chart also decorates each node reflecting the mix. And finally, each node is labelled in the top left with a number. This reflects the majority class in that particular node. In this case, 0 represents repayers and 1 represents defaulters. Below this 0 or 1 label, we see the percentage of records in this node of that class. As well as our root nodes and our leaf nodes, we also have branch nodes. These have data both coming in and going out. The root node and branch nodes pose a binary question, the answer to which will send data down one path or another. The question posed is summarized at the bottom of each node. The answer is written on each path, and the thickness of the path is proportional to how many records match that answer. We can perhaps see all this a little clearer if we reduce the depth of our tree to 4. Here it's easier to see that our root node contains 80% repayers and 20% defaulters. the first question to divide the data is based on credit rating or grade. The lowest rated borrowers, the 3s through the 7s, go down the left-hand path. The highest rated, these are the 1s and the 2s, go down the right. We can see that there are many more 3s through 7s than 1s and 2s based on the relative thickness of the paths emerging from our root node. At the next level, the tree has decided to pose a different question for our low credit rating branch compared to our higher rated one. For the lower quality credits, the question is based on the amount of late fees already received. Larger late fees go to the right, negligible or zero late fees to the left. While the amount of late fee payers is small, look at the relative thickness of the lines, this group of borrowers is overwhelmingly in the defaulters category. I hope that this simple illustration is starting to show the power of decision trees. We can see the criteria that are leading to a decision. The color coding, the pie charts, the thicknesses of the lines all help us in quickly grasping the key clarification criteria and the combinations of criteria that form a decision. If we zoom out from this micro view with a depth of 4 to a more macro view with a depth of 6, we can start to see these combinations as patterns. Here we have combinations that are characteristic of the default, while here we have combinations that suggest that borrowers repay. The ability to quickly switch focus from the macro view with its patterns to the micro view to look at specific tipping points is another great white box feature of decision trees. So, given our test data, how do we design the questions and in what order to get the best performance? Well, there are lots of approaches, and you'll hear terms like Shannon entropy and information gain. Here we're going to focus on a technique called Gini impurity. It's popular, quick, and of all the methods is perhaps the most intuitive. As a practical matter, there's usually very little difference between the methods. But as with all things AI, it's worth experimenting to see if different methods suit your problem domain better. The equation for Gini impurity is shown on your screen. If you have k different things that can happen in a population D, then the Gini impurity is 1 minus the sum of the square of the probabilities. That already sounds too daunting. Let's make it a little simpler. In our case, for our population, we have only 2 classes, defaulters and repayers. So that can simplify the equation a little. It's perhaps even less daunting and more understandable if we expand it. Then it becomes 1 minus the likelihood of a default squared minus the likelihood of a repayment squared. So as a quick example, think about the Gini impurity of our root node. Here we have 80% repayers and 20% defaulters. So the probability of picking a repayer at random from this node would be 80%. And likewise, a random drawing from this group would be a defaulter 20% of the time. If we plug these values into our Gini impurity equation, we can see that the Gini impurity of the root node is 0.32. This root node is impure as it has both repayers and defaulters in it. By looking at the equation, you can see that you get an impurity of 0 only when the population just contains one class. That is to say, a pure node. The way that we will apply the equation is to look at the 2 resulting nodes that form for each question. As the 2 nodes will likely have different numbers of members, we'll look at the weighted average impurity of both nodes. The formula for the weighted average is shown here. The lower the Gini impurity, the better. The lower the Gini impurity, the purer the nodes. Or, put another way, the nodes will be deeper red and deeper blue in colour. So let's work through a few examples on a highly simplified dataset to drive this home. As ever, pause and ponder and make use of the rewind button as often as you need to. So here's the very simplified dataset of our loan default information. We have 16 rows. Our target variable is shown in green. Whether the borrower defaulted, a 1, or repaid, a 0. And we have 3 input values: the debt to income ratio, which is numeric, the credit rating, a categorical variable, and a previously defaulted flag, which is a binary yes/no. Let's start with this defaulted flag, as it's the simplest. In this sample, there are 7 borrowers that have previously defaulted and a total of 9 borrowers that haven't. Looking through the records of the previous defaulters, we can see that 5 of these repaid their loan, while only 2 of them defaulted for an additional time. In the other path, we have 4 repayers and 5 defaulters. So, if we apply our Gini impurity to each branch node, we get 0.4082 for our left branch and 0.4938 for our right branch. We can then get the weighted average with the formula on your screen. This gives us the weighted average Gini impurity for this question to be 0.4563. Now let's turn attention to our rating feature. Let's split by the top credit rating, which is an A. All the A's will go on the left path and the lower rated borrowers will go on the right. There are 4 records that have the top credit rating and none of them are defaulters. Of the remaining 12, 5 repay their loan but 7 do not. Let's look at the Gini impurity of both branch nodes in this case. The Gini impurity of the left branch is 0. We have a pure node, while the Gini impurity of the right branch is 0.4861, a mixed up node. If we look at the weighted average impurity of this total result, we get 0.3646. This is better than the split based on previous default, as it gives us a lower impurity score. Rating is a categorical variable and there are many other questions we must pose. Let's this time make our split based on the lowest credit rating and look at all our Ds. Of our 4 Ds, all are in the defaulter category, with the remaining A's, B's and C's, 9 repay and only 3 default. Once again, we have a pure node on the left with a Gini impurity of 0, and on the right, a Gini impurity of 0.375. This gives us a weighted average Gini impurity of 0.2812, our lowest thus far. But as a categorical variable, we have to look at all the splits on single ratings as well as the combinations of ratings. These are shown on your screen. So, several points to discuss here. Firstly, you should see a symmetry in the results. The weighted Gini impurity for a split on A is identical to a split on B, C and D. Well, it should be. This is the same split. So as an optimization, we don't need to go through all the combinations. Secondly, the split on D, or its mirror image, A, B and C, is the lowest. So if we turn to numeric data, we have to approach this slightly differently. The first thing we need to do is to reorder our data for the column in question. Then we simply work through our data row by row, splitting based on being greater than or less than or equal to this value. So we'll start with a debt to income ratio of less than or equal to 4.02. We can see here that once we've worked through the now familiar equations, we get a weighted Gini impurity to be 0.4666. If we fast forward to a debt to income ratio of less than or equal to 11.48, then we see 6 records in our left branch and 12 in our right. These are some of the highest Gini impurities we have seen, as the data is very evenly distributed. The weighted Gini impurity here is 0.4875. Hopefully, having gone through the numeric data, you can now see a further optimization we could have made to the rating data. As the rating data is ordinal, we could have used the same approach for this category as we have for the numeric data. We don't have to go through all the unique combinations as we would for nominal data. Now, this is a toy data set for illustrative purposes. You would never build a workable decision tree from such a small sample. But to complete the illustration, let's look at the decision tree built from this data. You can see here that the split on rating D was indeed the optimum first question. It was followed by a split on the A-rated borrowers. A couple of further debt to income ratio splits managed to segment all the data. So if we ditch our toy data set and return to our cleaned loan data set, we can see the effect of the ordinal ranking of the rating category. The A to G ratings codes have been converted into numeric codes, and we can therefore split by rank rather than combinations. Let's also look at training and testing on this data set. This has nearly 20,000 rows, 14 features and 1 target variable. In building our decision tree, we start at the root and determine the split that results in the lowest weighted Gini impurity in the first 2 branch nodes. We've already seen that the optimum split is based on credit rating, with borrowers in the highest 2 credit scores being separated from the rest. We then recursively apply the same approach to determine the best split for each branch node all the way down the tree. So you might be wondering how long all this might take. Well, as with all AI models, it's the training that takes the time. For this dataset, the training time is just over 4 minutes on a 2020 MacBook with 8 gigabytes of RAM, a very modestly equipped machine. So, to summarize, decision trees are a vital component in the machine learning toolbox. Unlike many other AI techniques, they are very transparent in how they classify data. The rules that they learn during training can be explicitly described in a tree viewer. During training, decision trees learn to ask a series of questions that will separate the data into distinct classifications. The questions are ones with binary outcomes: yes, no, greater than, less than, member or non-member of a particular set. These questions split the data into smaller and smaller groups. Rather than choosing questions at random, the decision tree does an exhaustive search of all possible questions. In this video, the question chosen is the one that splits the data into 2 groups with the lowest weighted average impurity. Other methodologies exist that look at information gain or entropy. Different methods typically don't lead to wildly varying results. We've seen in this video how to apply the Gini impurity measure to different data types: binary data, categorical codes, and numeric values. Each data type has its own methodology, but the outputs are comparable, as they are always impurity measures. Viewed close up, decision trees allow inspection of decision boundaries to classify data. Viewed from a distance, decision trees show how multiple factors combine, often in subtle ways, to perform classification. This is Richard Walker from Elucidate. Many thanks for watching. Please join me in the next video, where we will look at another popular machine learning tool: support vector machines.